that is a bit more stringent that leads to larger values of the required sample size, but because machines are so fast these days, we can afford to take those larger samples as well. So all I've been doing in part one of this is just asking the Monte Carlo standard error to be around some tolerance like 0.001. Now let's do something a little bit more stringent. Let's say, suppose I wanted theta bar star to differ from the true mu by no more than a number like I did before, epsilon 1, which might be that same 0.001 as before, but I want that to occur with Monte Carlo probability at least 1 minus some other error tolerance. So in other words, I could pick epsilon 1 to be some number like 0.001 on the scale of the data, and I could pick epsilon 2 to be some small tolerance on the probability scale like 0.05, and then this would be a more stringent requirement than what we had before because we're asking this thing to occur at least 95% of the time with respect to Monte Carlo randomness. So what we know from the central limit theorem and the calculations we already have done, that in repeated sampling, theta bar star is approximately normal with mean mu and variance sigma squared over m. And when you take those facts into account and make them operational, equation 4 becomes equation 5. The solution to equation 4 becomes equation 5. Where phi inverse of blah blah is just the that particular quantile. It's the place on the standard normal curve where 100 times the phi inverse of q is the place that 100q% of the area is to the left of that place. So if you look at the form of equation 5 and compare it with the form of equation 3, and the screen is not quite large enough to make that easy to do, equation 3 says sigma squared over epsilon squared, and equation 5 says sigma squared over epsilon 1 squared, same structure, except you have to multiply by a number from the normal curve that's squared in the numerator. And if we usually use a number like epsilon 2 is 0.05 for 95% Monte Carlo confidence, then the normal number that gets you about 95% in the middle, as you know, is 1.96, which is around 2, and 2 squared is around 4. So that says that we should be using a sample size that's like the one we had before, but around 4 times larger. So this is a more stringent requirement. And so here I take the previous number, 148214, and I multiply it by 1.95 blah blah squared. And it turns out that we would have to have a sample of size about 569,000 to get that degree of Monte Carlo accuracy. On the other hand, that's really fast. So let's go back to the web page, and here I'll ask R to do such a thing. Take one data set of size 569,358 and get me the Monte Carlo estimate and the Monte Carlo standard error for that estimate. And watch how long it takes to do that. Here we go, ready, and it comes back instantaneously. And so our machines are really fast these days. Not for all calculations, of course. In the past few days, in some of the work I've been doing with my colleagues at Kaiser, I've been fitting logistic regression models where the data set has about 12 million observations in it, and there's on the order of about 100 predictors. And that calculation, it got some distance into the calculation after doing a whole bunch of preliminary things to get my predictor variables ready. And then after about 7 or 8 hours, it just fell over. Stata just froze. I was using Stata for that. It just froze. So for some purposes, 569,000 is a tiny sample size. For other purposes, 12 million is too big for the hardware and software sitting in front of me right now. So it's it's all relative to what you're trying to do. But so we end up deciding on the basis of this that we think that because the Monte Carlo standard error with this run was on the order of 0.0005, that's a very good Monte Carlo standard error for being able to say something confident about 3 significant figures to the right of the decimal point, because basically those first three there are pretty solid if the standard error is on the order of 0.0005. And so I would report 2.071, give or take about 0.0005 would be my Monte Carlo summary of what we've learned here. And so, okay. Now, let me show you we're about to go into wind bugs later today. Let me actually go there now. So here's, where are you, wind bugs? There you are. And they have a thing in here called help. And help includes a whole bunch of examples. This is really wonderful software. They have a tremendous set of examples. But if you look at their runs, they give an example. So here's a hierarchical model. And we go blah, 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 blah. And look what they've done. They've, later on I'm going to tell you what a burn-in is, but they've used a monitoring value. This is their value of M in this example of only 10,000, and yet they're reporting 4 significant figures everywhere you look in the table based on a Monte Carlo run of only 10,000 draws. And what's going to be worse, as you see later today, MCMC works in a way that has less Monte Carlo accuracy than IID sampling does, often substantially less. And so this is a laughably small number of iterations to be able to try to report 4 significant figures. And it's everywhere in the documentation for wind bugs. They make you think that you can run MCMC with a tiny sample size and then be able to report huge numbers of significant figures. And we just saw a minute ago that's not true. To get something like 4 significant figure accuracy in this problem using IID sampling, I needed 500,000 draws. And so there are very few things I could say that would be a legitimate knock on the wind bugs people, but that's one of them. They were a little bit shoddy in the way they wrote up their examples because it makes people think that they've got more Monte Carlo accuracy than they actually have. Okay. So I just say here, it's evident from calculations like these that people often report simulation-based answers with numbers of significant figures far in excess of what is justified by the actual accuracy of their Monte Carlo estimates. And what we'll see when we run wind bugs later today is that it produces Monte Carlo standard errors, and you can decide for yourself how large the M should be. All right, now I actually made that look pretty easy because there was already a function inside R called R gamma that did samples from the gamma distribution. If you run the clock back to 1942 and you're sitting around like Mr. Metropolis and Ulam were, there aren't any computers yet. There is no R. You have to figure out how to do random sampling yourself. And so how would you go about writing a function like that to simulate from a given specified distribution? And I raised this question not just historically, but understanding how the main idea that people use for this, how it works, will be central to our understanding of how MCMC works. So let's just humor me on this. There are a number of general purpose methods for generating random numbers, and I won't go anywhere near a full survey of them. But the one particular idea that we need to look at to understand how MCMC works is the method that the brilliant mathematician John von Neumann invented. He published it in 1951, again, because the military wouldn't let him publish it during the war. But he invented it around the same time as Metropolis and Ulam. They were all working on the same project. And so he did this about 1942. He called it rejection sampling. And when you can pull it off, if you're trying to make IID draws from a distribution, it's often one of the most computationally efficient ways to do so. So I'll give you an example, and then we'll see how to build a rejection sampler that would work in this problem. I have data from a study that was done at UC Berkeley in which a survey was taken of bicycle and non-bicycle traffic in a bunch of streets near the UC Berkeley campus. And so what they did was they chose 10 city blocks on residential streets with bike routes. They chose them at random from all such blocks at Berkeley. And on one of those particular blocks, little n vehicles were observed on a randomly chosen Tuesday afternoon from 3 to 4 p.m. And little s of them were bicycles. And so this is one of these Bernoulli situations, right? Because every vehicle either is a bicycle or not. And when you count how many bicycles there are, you get a binomial. And so a standard model here would be to draw inferences about the underlying proportion theta of bicycle traffic, proportion of bicycle traffic, PBT, on blocks similar to this one at times similar to Tuesday afternoons from 3 to 4, then you would build a model like we did with the heart attack case study. You would say, capital S, the number of bicycles you saw, if you knew what theta was a single draw from a binomial distribution with parameters n and theta. And then if you can quantify your external information about theta by means of one particular member of the conjugate family, the beta family, with parameters alpha 0 and beta 0, then we know from our previous work with Bayes' theorem and conjugate updating here that the posterior for theta, given the actual number of bicycles little s, will be another beta distribution, and alpha 0 updates to alpha 0 plus s, and beta 0 updates to beta 0 plus n minus s. That's the stuff we learned several times ago. Provided, of course, that whatever prior information I have about theta can be meaningfully captured by one member of the beta family. So I elicit from myself my information about this. I used to go to Berkeley as a grad student. After reflection, I realized that thinking about residential city blocks with bike routes in Berkeley, I'd be quite surprised if the proportion of bicycle traffic on a Tuesday afternoon between 3 and 4 was substantially less than 5% or substantially more than 50%. And in particular, I decided to quantify that by putting 90% of my prior mass between those two values, and then putting half of the remaining prior probability in the left tail and half in the right tail. And you can use numerical methods like the ones I showed you before that I'm thinking about a beta prior with parameters 2.0 and 6.4. This distribution has prior mean at about 24% bicycle traffic and prior standard deviation of about 0.14, so it's a rather diffuse prior, but there's a little bit of information in it. And in the city block in question, there were 74 vehicles, of which 16 turned out to be bicycles. And so the posterior comes out alpha 0 plus s, which is 18.0, a beta with parameters 18.0 and 64.4. Now, again, let's pretend, for the sake of illustration of rejection sampling, that we didn't know the formulas for the mean and standard deviation of a beta distribution. In fact, we know the answer is alpha over alpha plus beta, so 18 over 18 plus 64.4 is the right posterior mean. And suppose that you wanted to use IID Monte Carlo sampling from that particular beta posterior distribution to estimate the posterior mean. Well, here's Mr. von Neumann's idea. And it relates to something that somebody said earlier. Suppose that the target density of interest to you, P of theta given y, suppose for some reason it's difficult to sample from. But instead, you can find another density that is easy to sample from and that has the important property that the new curve that you draw dominates the distribution you're interested in the sense that it's always at least as high as the distribution you're interested in. Now, I'm going to call this new thing an envelope function, capital G. And capital G does not have to be a density, but it needs to be something that could be normalized to become a density. So think of it as just an unnormalized density function. And suppose that this is what the picture looked like. So the curve in solid there is the actual posterior we're trying to draw from, which for some reason is difficult to draw from. But we can construct one of Mr. von Neumann's envelope functions, capital G, that everywhere dominates lowercase p. You see how it's always at least as high as lowercase p. And has the property that when you density normalize capital G, it is a distribution that's easy to sample from. So then he can tell us how to sample from P by sampling instead from capital G. That's his idea. And so it's like what we were talking about when this gentleman asked me a question a while ago. Little p is hard to sample from, but I can find another density that's easy to sample from. Then I can use the draws from G to help me make valid draws from P. So that was von Neumann's idea. And here, the reason it's called rejection sampling is the following. He says, okay, make a draw theta star from the normalized version of G, namely lowercase g. Let's call that draw theta star, and then either accept or reject that draw according to an acceptance probability, which I'm going to call alpha subscript capital R of the value of theta star given y. Alpha is going to be our acceptance probability. A subscript capital R just says it's the acceptance probability for rejection sampling of the value theta star. And von Neumann says, okay, here's the way the game is going to be played. Decide to accept or reject according to an acceptance probability, by which I mean you, in effect, you toss a Bernoulli coin with a success probability given by alpha R. And if it comes up as success, you accept the draw, and if it doesn't, you reject the draw. And his idea about what to do when you reject the draw is you throw it away completely and draw again until you get a draw that you want. And then keep doing that same thing over and over again until you have as many such draws as you'd like. So that's his idea. If you can't figure out how to sample directly from P, then go ahead and sample from G, which you know how to sample from, and then toss Bernoulli coins to see whether you accept the draw from G or not. Pretty cool, indirect sort of idea. Now all that remains is he has to tell you what that acceptance probability is. And he showed that the following choice. You find theta star along the number line, and you evaluate the height of the target density, P, at that place, theta star, and you evaluate the height of the envelope function, G, at that same place, and the ratio of those two things becomes your acceptance probability. And the reason that that's the right thing to do is actually pretty straightforward to see. If I try to sketch this over again over here, so here's P, and here's the envelope function G. So here's my lowercase p, and here's my uppercase G. Pick a theta star from G, and it lands right there, for example. If you wanted it to be a valid draw from P, then if you thought of the place theta star as the first coordinate of a two-dimensional place there, imagine taking that theta star and extending it up that far, for example. Well, if the theta star with respect to this second coordinate fell underneath the curve called P, then you want to accept it because it's been driven by P. But if instead it fell in this region that's governed by G but not underneath P, you'd want to reject it. And so how do you decide to reject something with probability that's the right size? Well, you see how big the height of the target is at the theta star, and you compare that with the height at G. And what that will do, in effect, is it's asking you to make a two-dimensional draw underneath the envelope function and get a point, and then look at see whether that point is under G. Of course, it has to be under G, but see if it's under P also. And every time it falls under P, you accept it, and every time it falls above P, you reject it. So that turns out to be his algorithm, and it works. So just like it says here, making a draw from the posterior distribution of interest is like choosing a point at random in two dimensions under the density curve P in such a way that all possible points are equally likely, and then just writing down its theta value. If you instead, pardon? Oh, I'm sorry, thank you. That's a very bad habit. Yeah, please jump on me as fast as possible when I do that. I'm going to try to do better. So making a draw from the posterior distribution of interest is like choosing a point at random in two dimensions under the density curve lowercase p in such a way that all possible points are equally likely, and then just writing down the theta value that you got. If instead you drew from capital G so that all points under capital G are equally likely, you have to throw away all the points that fall between those two curves to get correct draws from P, and this can be accomplished by accepting each sampled point with probability given by the ratio of the height of P versus the height of G. So it's a cool idea, and it works. So here's a little block, here's a little pseudocode block that summarizes von Neumann's idea. So this is rejection sampling to make little m draws at random, in fact, in an IID fashion, from the density lowercase p of theta given y for real valued theta. And so far this algorithm, I only sketched the picture with real valued theta, but it turns out to work for a vector of theta as well with no changes. But let's just talk about real valued theta for the moment. Select an integrable envelope function G. So I should have mentioned that before. G has to, oh, and I did say it, G has to be normalizable, and so that's what I mean by integrable. Its integral has to be finite so that I can divide through by that finite number and make it into a density. So select an integrable envelope function G, which when normalized to integrate to 1 is something that later on we're going to call your proposal distribution, lowercase g. And it's an envelope function, capital G, because it's everywhere at least as large as lowercase p. And now we define the acceptance probability the same way I showed you before. And now here's 1, 2, 3, 4, 5, 6, 7, 8 lines of pseudocode that does rejection sampling. Initialize your counter of how many valid draws you have. Let's call it T so far. Initialize it to 0. And repeat the following until you've achieved the m draws that you want. First, take a sample theta star from the density lowercase g. then sample U as a uniform random draw, and if U falls below the rejection probability, then you accept. So that's a way to make a Bernoulli coin toss, right? Do a uniform and see if that number's below whatever the success probability was. So if U falls below, at or below the rejection probability, the acceptance probability rather, then you update your vector of draws. Theta t plus 1 is given the value theta star, and the t is incremented to t plus 1. And then keep doing that until you have m draws. There we go. And so how can we build an envelope function? Well, that's, of course, the trick here. Von Neumann's approach gives us immense freedom in choosing the envelope function, which when normalized then becomes the proposal distribution for the more general MCMC story we're going to look at later on. Von Neumann's story says you can use any envelope function you like as long as it is an envelope function. In other words, as long as it's, when normalized, is a proper density, and when unnormalized, lives everywhere at least above, never below the target. So if you look at members of the beta family, they look like this, and so that's going to be our target. So this is the theta here, and this is the scale P of theta given Y, so that's the posterior. That's our target. It's not quite so easy to see how to build an envelope on the scale of the density, but what if I took the logarithm of the density? Then what would this function look like then on the log scale? That's what you can start asking yourself. And it turns out to look like this. So if I can come up with a simple way to build an envelope on the log scale, then of course I can translate that envelope up to the scale of the data just by exponentiating. So what would be a simple way to build an envelope on the log scale? How about straight lines? So for example, pick one point over here that's to the left of the mode and draw a tangent to the curve at that point. Pick one other point over here that is to the right of the mode and draw another tangent to the curve right there. So I didn't draw that very well, but you get the idea. And look, there's our envelope. The envelope starts right here, and it goes along until it reaches that point right there, and at that point it switches over and starts and goes down like that. Do you buy that that's an envelope on the log scale? And now, what's cool about that is if it's built up of line segments on the log scale, when you exponentiate line segments, you get piecewise exponential distributions, which are easy to sample from. So this is a pretty cool idea. This was not von Neumann's idea. This was an idea due to Wally Gilks in Cambridge in England, but it's a nice idea. Moreover, having built an envelope on the log scale with two such lines, can we do even better? Well, when do you know an envelope is really good? Intuitively, you don't want to reject very often, right? Because every rejection in von Neumann's algorithm is wasted CPU time. So what would you like the envelope to be in relation to the target? As close to it as possible while still remaining always above it, right? And so what's that correspond to down here? Same thing, right? So how could I use the same idea and make an envelope that's even tighter than this one? More line segments, right? Pick another point that's sort of near the mode, throw in another tangent, and now the envelope is tighter. Now instead of going up there, now I just go across like this, and I go across until I grab that one. And you could keep doing this if you want. Pick more and more points, and you'll build a tighter and tighter envelope. This is called adaptive rejection sampling, because every single point you make that you draw from the distribution becomes a new place to draw a tangent. So adaptive rejection sampling. However, it only works when the logarithm of the density is such that the tangent always lies outside, right? And so what's the name for that in math? Concave. So this function here is called log concave. Rather, I'm sorry, this function up here is called log concave because its logarithm is concave. And so it turns out that, so Wally's idea, adaptive rejection sampling, I don't know if that was a kind of a joke on his part, because the acronym for it is ARS, and that's nearly a bad word in British version of English. But his algorithm only works if the density you start with is log concave. But fortunately, many, many, many standard densities do have the log concave property. And so there's a kind of nice way to build an envelope and get your rejection sampling up and running. Yes, please. Well, this has all been rather artificial, because whenever you have a one-dimensional density, by definition, it's probably not going to be that hard to sample from. Is particularly if you have a simple formula for it. Although if I gave you some really weird density and asked you to sample from it, it wouldn't be immediately obvious how to do that, I think, without using... Okay, but so if you spot me first, the premise that P, the target, is hard to sample from, and that could actually be true. If I gave you some very weird density, even in one dimension, it might be a little bit uncomfortable for you to quickly develop an algorithm to correctly sample from it. The thing that makes this algorithm work is that with the use of adaptive rejection, is that the envelope on the log scale is a series of straight lines. And therefore, when we exponentiate that and get e to the minus stuff and so on, what you're getting is a series of piecewise exponential distributions. And they're very easy to sample from. So that's the trick. So here we go. The top panel here is the log density, which it turns out in the beta family is log concave. And so I've chosen a point to the left of the mode and a point to the right of the mode. In order to make the envelope as tight as possible, it's going to turn out, and you can tell intuitively this would be sort of obvious, you want to integrate the function capital G and make 1 over the integral as small as possible. Is that, or make it as large as possible? Let me get this right. No, you want to maximize the marginal probability of acceptance of any single draw, which can be shown to be 1 over the integral of G. And so we want that to be big. And the way we make that big is we make the envelope be really skin tight against P. It always has to be at least as big as P, but we make it skin tight as we can. And so it's a little calculus problem, a little calculus of variations problem, actually, to work out, if you spot yourself only 1 point to the left of the mode and only 1 point to the right of the mode, what are the optimal places to locate them to make 1 over the integral of G as big as possible? And I won't show you the details of how to do it, but you get those points that I put there in little black dots. And so now if we go back to the density scale and exponentiate, see how it's a series of scaled exponential distributions? And so there you go. So there's Wally's idea of adaptive rejection sampling. Yes, please. That's a really good question, and I will try to work that out for you over one of the breaks. I've forgotten the answer to that question. It is possible, I think, that some of the members of the exponential family are not log concave, but I'll try to work that out. Real good question. So let's agree that what we mean formally, a real valued function is log concave if its second derivative on the log scale is everywhere less than or equal to 0. So that has the bowl-shaped down thing happening. Okay, so, and I've already mentioned that you want to make the acceptance probability as large as possible in the rejection in Mr. von Neumann's algorithm. And so you should minimize the area under the unnormalized envelope function subject to the constraint that it dominates everywhere. And of course, that certainly makes good sense. And those turn out to be the optimal points. And it turns out the acceptance probability is about 75%. Kind of interesting when you look at this bottom picture that it's quite tight over a very broad region. And yet that not so little triangle there leads to a rejection rate of about 25%. And so to make that tighter, I would want to, as you guys said, just start adding more points to build the envelope a little tighter. Okay, so I made a preliminary sample of M0, let's call it, 500 IID draws from using the rejection sampler. And I got a theta bar star of 0.2197 and a sigma hat of 0.04505. And then I worked out where things were. And already with only 500 draws, that sigma hat over the square root of 500 is already on the order of 0.002. So even with only 500 draws, I've already gotten quite a lot of accuracy about the posterior mean here. But suppose, as we had before, that I want theta bar star to differ from the true posterior mean mu by no more than some tolerance epsilon 1 that might be even smaller than 0.002, and with Monte Carlo probability at least, let's say, 95%. Then I can use that equation I showed you before. For instance, to pin down 3 significant figures in the posterior mean, given that the answer comes out 0.2197, that means I have to get things right out to the first 3 the first 3 digits to the right of the decimal place, and a rather small error in the 4th decimal place. So I might take the error tolerance on the scale of the data to be 0.0005, and then 95% Monte Carlo confidence. And that yields a recommended IID sample size of about 31,000. And there's no need to waste the previous draws. They were certainly valid IID draws from before. So if I want to end up with 31,200, I subtract 500 from that and get 30,700 new ones and just merge the resulting new draws with the old ones. And this is virtually instantaneous. And the answer comes out 0.21827 with a posterior standard deviation of 0.04528, and the Monte Carlo standard error therefore comes out 0.00026. And I would announce that I think the posterior mean is about 0.2183, rounding to 4 significant figures, give or take about 0.0003. And in fact, when you go back and do the arithmetic in the beta family, the right answer is 0.2184. So that's bin rejection sampling, except that there's something else cool that you can do. Other aspects of the posterior are equally easy to monitor. Yes, please. Sure. You calculate that by taking the actual, to work this method, you have to have an analytic formula for lowercase p and an analytic formula for capital G. And once you have those 2 analytic formulas, you simply form this ratio right here. And so it says you work out the height of the density, the target density at a particular point that you're thinking about accepting or not, and you work out the height of the envelope function at that same point, and you take their ratio. And then you toss a Bernoulli coin, and you use that as your success probability, and you accept with that particular success probability. So that's the idea. And the reason it works is the story I told a little while ago. This corresponds to the process of choosing a point at random in a 2-dimensional fashion underneath capital G, and then looking to see what its theta coordinate was, and then also looking to see whether that point lands above or below the target. And basically, if it lands above the target but still below the envelope, all those places I want to reject, and all the ones that fall below the P I want to accept. And the way to do that is to go ahead and calculate the ratio of the height of P at that particular point I'm thinking of accepting and the height of capital G at that point, take that ratio and use that as my Bernoulli success probability. That will reject all the draws that are out there and keep all the ones that are in here. So it works. It's just a good plan and it works. Okay. Now what I was about to show you is that other interesting aspects of the posterior are equally easy to monitor. For example, if I wanted a Monte Carlo estimate of the posterior probability that theta was less than or equal to some specified number q, then I could, once I've got my Monte Carlo sample, I just work out the proportion of those values in the Monte Carlo sample that are less than or equal to q. But look, here's a slightly slick way to write that provides us not only with the right answer, but also with the Monte Carlo standard error. So far, what I've got is I've got the Monte Carlo data set that has a theta star column in it. And if I'm wondering, for instance, about the posterior probability that theta is less than or equal to 0.15. Maybe the first number comes out 0.17, and the next one 0.11, and the next one 0.48, and blah, blah, blah like that. Look what cool thing I can do. I can create next to that an indicator function for whether the theta star is in fact less than or equal to 0.15. So I can add a new column to the Monte Carlo data set. And here I get a 0 right there, and I get a 1 right there, and a 0 right there. And the nice advantage of that is that when I'm done, the mean of these 1s and 0s is my Monte Carlo estimate of the probability that theta is less than or equal to 0.15 given the data and the background information. Now, so far I haven't done anything that's any better than simply sorting the theta stars from smallest to largest and just counting how many of them are below 0.15. But the cool thing is that having written it in this fashion here, this thing is a mean. And so I can come up with a Monte Carlo standard error for this particular estimate just in the same way I did for calculating means beforehand. The Monte Carlo standard error turns out to be square root of p hat 1 minus p hat over m. And so I not only am able to monitor this other aspect of the posterior I'm interested in, I'm able to come up with a Monte Carlo standard error directly to figure out how accurate that estimate is. And if I do that with my 31,200 draws I showed you a minute ago, the p hat for this particular posterior comes out about, there's only about a 5% chance of having a proportion of bicycle traffic no larger than 15%. And my estimate of that quantity has a Monte Carlo standard error of 0.0013. Now, if you compare that number, let's see if I can squeeze it in up here. Look how when I had 31,000, oh, sorry, I did it again. Look how when I had 31,200 draws and I was interested in the posterior mean of the distribution, I was able to pin that down with a Monte Carlo standard error of about 0.0003 with 31,200 draws. But when I'm interested in one of these percentiles or quantiles down here, or percentile in this case here, the Monte Carlo standard error is much larger. It's about 10 times larger. Used to be, well, I guess it was that about 4.5 times larger. Used to be 0.0003, and now it's 0.0013. So 13 divided by 3 is about 4. So what's going on here is something that you may or may not have ever noticed before. Percentiles are harder to pin down with equal Monte Carlo accuracy in terms of significant figures than means or standard deviations. And the reason is that is seen by looking at how I got it with this table over here. It's the mean of a bunch of 1s and 0s. And I don't know whether you've ever thought this through before, but the binary scale, outcome scale, is a much less information-rich scale than a quantitative scale. If I offered you a chance to measure something in shades of gray all along the number line, and I offered you instead the chance to just find out whether that number in question is bigger than 6 or not, you've lost a tremendous amount of information. If I offered you that first thing and then denied you that and gave you only the information about, the binary information about whether the number was bigger than 6 or not. So you see how the 0-1 scale as an outcome scale is much more information poor than the actual quantitative continuous scale that ends up being dichotomized to produce 1s and 0s. And that shows up here. The Monte Carlo standard error is bigger by a factor of 4. And in fact, if I wanted a Monte Carlo standard error for that p hat value of 0.001, you can use the formulas to show that I would need an IID sample of about 5 million draws. And that sounds like a lot, but it still only takes a few seconds at the sort of speeds that we're using these days for our machines. I have seen Markov chain Monte Carlo examples where on the order of 10 to 20 million draws were needed to get decent Monte Carlo accuracy. Most of the time, though, for most of the examples I'm going to show you in here, until we get to the Bayesian non-parametric stuff later on, a sample monitoring run of 100,000 to 500,000 draws is plenty enough to get the sort of accuracy that you need. And you can achieve that in clock times for most models with the machines we have these days in a matter of minutes, not hours or days. All right, so that's Mr. von Neumann's idea about rejection sampling. Terrific idea. Works great when the density that you're trying to learn about is one-dimensional. But of course, what we saw in the earlier part of thinking through what would happen in problems with parameter vectors rather than just scalars is that your appetite for complexity grows, and you will quickly find yourself being interested in posterior distributions on vectors that are of length 10 or 50 or 100 or 500. And it's a very sad fact about Mr. von Neumann's approach that as the dimension of the vector that you're trying to learn about increases, it becomes increasingly difficult to find an envelope function. It's just harder in high dimensions to guarantee that the function you hope to use as an envelope is in fact everywhere at least as large as the target that you're interested in. You can't really sketch it in 10 dimensions and make sure that you've sketched it high enough, for example. So, like it says here on this page, nothing in the Metropolis-Ulam idea of Monte Carlo estimates of posterior summaries requires that these estimates be based on IID samples from the posterior. The second ID part of IID is necessary, at least for simple implementations of this sort of idea. But the first I, it turns out, is not necessary. And this is lucky, because in practice, it's often difficult, particularly when theta is a vector of high dimensions, to be able to find that envelope function that Mr. von Neumann tells us we have to have. So to get to the idea that's being used everywhere today, we have to relax the assumption that the theta stars are like IID draws from the posterior, and to consider instead what is the next thing up in complexity from an IID sample. So now I ask you to think, if you've ever studied anything having to do with time series, a series of numbers as a time series is what people call white noise in the time series world when the draws are IID from some underlying process. So von Neumann says, you got to make your draws in a white noise fashion. And the hallmark of white noise IID draws, when thought of as time series, is that the correlation of what's happening right now in the series I'm watching of these draws, and the correlation of what's happening right now with what happened recently is what? By definition, if they're really IID draws, then the correlation is 0. What if we have to abandon that because it's too hard to build the rejection envelope? What's the next level of complexity up from that? Well, somehow you want the time series to depend upon itself not very much in the past. You're going to start allowing it to depend on previous values of itself, but somehow not very much. Pardon? Yeah, you might try something like the following. You might try to create, and what we're about to build is something, the general name for which is a stochastic process, and that just means a bunch of random variables or a bunch of uncertain things indexed by something. In this case, we're going to index it by time. Why not build a story involving a stochastic process where to decide where it goes next, you only have to know where it is now. With an IID process, to decide where it goes next, you don't even have to know that. You just make another draw, because they're all IID. But the next level of complexity up from that would be the one I just mentioned. A stochastic process that has the property that to decide where to go next in generating the next value, you only have to know where you are now. And the name people give for that is a Markov chain. In fact, it's called a first-order Markov chain because you only need to know one period back to know what to do next. And so that was what I'm imagining what Metropolis and his colleagues did. They said, well, Mr. von Neumann's idea is great, but it doesn't work in high dimensions. So let's try to relax the IID part and try to build a Markov chain instead, a first-order Markov chain, and hope that we can get the right thing to happen. So now we're about to relax the assumption, like it says here on this page, that the theta stars are IID from the target posterior distribution, and instead to consider samples theta 1 star through theta m star that form a time series. And all I mean by that is you want to imagine, now we're imagining drawing the data set, not the data set, but the Monte Carlo data set in this fashion here. We're going to now imagine this is time going this way, and by that I mean iteration number. Pardon? Is it not high enough? Thank you. time t, I mean iteration in the process. And here I'm going to plot theta t star. So this, that sounds like the battery's starting to fade. I want to see what happens over time. And I can watch and see the thing unfold as a time series. That's an example of one particular kind of time series unfolding in a certain way. So that's the sort of thing that Metropolis and his colleagues wanted us to think about. Imagining the first draw, the second draw, the third draw, and so on, plotting them in time going this way, iteration number, and the actual value going that way. And now what we're going to do is we're going to think of them as a time series having the property that theta j star may depend on previous theta stars, theta j prime star for j prime earlier in the sequence. And what they did was this thing that we're about to look at now. They allowed for serial dependence, Metropolis and his colleagues in the Metropolis algorithm paper, they allowed for serial dependence of the theta j stars by combining von Neumann's idea of rejection sampling with concepts from Markov chains, which is a special case of the general theory of stochastic processes. And that gives rise to the name that we have for this technique now, which is not a name that was given to it by Metropolis and colleagues. Combining Monte Carlo sampling on the one hand with Markov chains gives rise to Markov chain Monte Carlo. Our British colleagues sometimes pronounce that Monte Carlo Markov chain rather than Markov chain Monte Carlo, but it comes out MCMC either way. So I need to remind you a bit about Markov chains. If you've never had anything about them before, don't worry. We don't need to know very much about them. And if you've had them before and it's rusty, don't worry again, because we don't need to know too much about them. So a stochastic process, a very fancy sounding phrase, it's just a collection of random variables indexed by something, by an element that runs across an index set. So I'm going to call them theta t star, t in some set capital T, and capital T is the index set, and here in this I've chosen T to remind us that it's going to stand for time, and by time I mean iteration number in the process of making sequential draws from the posterior. Now in practice, the index set capital T can be either discrete, for example the non-negative integers, or continuous, for example the non-negative real numbers. Markov chains themselves are a special kind of stochastic process that can either unfold in discrete time or in continuous time. Fortunately, we'll be talking here about discrete time Markov chains, which is all you need for MCMC, because we're never going to think about theta t star where t is equal to 1.17444. We're going to think about theta t star where t equals 0 or 1 or 2 or 3 or 4 or ... So the index is always going to be an integer here. Now, another complication, the possible values that a stochastic process can take on are collectively called the state space, capital S, of the process. And in the simplest case, capital S is real valued, in other words, one-dimensional, and can also either be discrete or continuous. And we need to be able to work with continuous state space Markov chains because we're simulating from continuous posterior distributions. So we need to have the state space correspond to the different possible values that the quantity of interest theta could take on. But I'm going to show you, as examples of Markov chains, I'm going to show you discrete state spaces because it's easier to think about them and the math is a lot easier. So the famous probabilist William Feller wrote a lot about Markov chains, and there's other people who have written about them also. Basically, whoops, I don't know how that happened. A Markov chain is a stochastic process that unfolds in time, and this is a slightly tricky way to say it, but you'll see what I mean. It unfolds in time in such a way that the past and the future states of the process are independent given the present. That's really what's going on with a Markov chain. And all that is a fancy way to say the following thing. To figure out where the chain is likely to go next, you don't need to pay attention to where it's been in the past. All you need to pay attention to is where it is now. And so we can formalize that with this definition here. Stochastic process theta star t, t in the index set capital T, where t, capital T here is the non-negative integers. That stochastic process with state space S is a Markov chain if for any set capital A in the state space S, the probability that the chain finds itself inside that set A at time t plus 1, given all the previous values of where the chain has visited, is equal to that same probability that you're interested in given only where the value of the chain last time. In other words, if I offer you the whole history of the chain from time 0 all the way to time t, and I ask you to predict what's going to happen at time t plus 1, you get to ignore everything except time t. All the previous stuff is irrelevant. So the Markov story is an important story with respect to how quickly the chain forgets its past. And the answer is, once you've arrived at time t, it forgets everything about where it's been before, and you only need to know a rule for deciding how to move from where you are at time t to where you are going to go at time t plus 1. That is the hallmark of a first-order Markov chain. Naturally, when you're studying things like time series, that would be an extraordinarily powerful simplifying assumption, because obviously if the general story was that you had the chain depended upon itself 50 periods back in time, that's got to be much more complicated than if it didn't depend on the past at all. It only depends on where it is now to decide where to go next. And so if you were trying to study stochastic processes and never studied them before, you would want to start with something like Markov chains, because it got to be easier than other processes. Now the theory of Markov chains is harder mathematically if S is continuous. Which, yes, please? Question or comment? Which is what we need, as I mentioned before, for MCMC with real valued parameters. But most of the main ideas come out pretty clearly with discrete state spaces. And so I'm going to assume discrete S in our discussion here. So here's an example. Here's a discrete time Markov chain with a discrete state space. We want to think about a particle like a ball, and it moves around, but it only lives on the integers. And I'm thinking about the integers that go all the way out to minus infinity and all the way out to plus infinity. And we start the ball off at 0. And so you could build all manner of Markov chains that describe how the ball could move from 0 to practically any other integer you could imagine. Did that come from my machine? Oh, okay. But I'm going to describe a very simple move strategy. Wherever the process is at time t, let's say it's at integer I, it tosses a three-sided coin, so to speak. There aren't any three-sided coins, but it tosses a three-sided coin, and it either moves backwards in the integers one step with probability p1, or it stays where it is right now with probability p2, or it moves 1 unit to the right with probability p3, where those numbers p1, p2, and p3 are strictly between 0 and 1, and they add up to 1. So those are called the transition probabilities for the Markov chain. Well, this is a special case of a general process. It's called a random walk. It's a random walk on the integers. Oh, this happened again. It's a random walk on the integers, and it's clearly a Markov chain, because in order to simulate where it's going to go next, all you need to know is where it is now. That's the basic idea. What is happening? Thank you, Mr. Bill Gates. You and your bloody machines. All right. Now, I need to tell you about more about Markov chains. Some of them are nice, and many of them are not very nice. And so I have to say what I mean by nice. And so it turns out that there are three main things that define a Markov chain being nice. First of all, they satisfy a property called irreducibility, which is a fancy word, but all it means that no matter where the chain starts, it has to be able to reach all the other possible states in a finite number of iterations with positive probability. So that's a requirement that means that the chain has a desire to mix freely amongst its possible values. All nice Markov chains are irreducible. All nice Markov chains are what's called aperiodic, and that just means that if you're thinking about how long it takes you to get back to where you are now, you can do that in any time period you want. It could be 1 time from now, it could be 2 times from now, it could be 3 times from now, whatever. and not things that there aren't any choices in there that are impossible. And I'm saying that very crudely, but here's the idea. Suppose I use this random walk here, but I force the ball to move either to the left or to the right, but not stay where it is. Then what's the smallest length of time it would need to get back to where it is now? If I forced it to either move to the left 1 unit or to the move right 1 unit, and I didn't allow it to stay where it is now, then the smallest number of steps that it would need to get back is 2. And in fact, if you looked at the all possible times necessary to get back here, they would all be divisible by 2. That would be an example of a periodic Markov chain with period 2. We don't want that to happen. Actually, it's not that bad if it happens, but it makes things much easier in the math if we don't have any periods. Formally speaking, the set of sojourn times, namely the times that you would need to get back to some state I having just left it, that set can have no divisor bigger than 1, so we want to get rid of those sorts of periods. It is true that periodic chains still have some nice properties, but we're going to rule them out. And I did that here by allowing the chain to stay where it is. That number P2 is positive. Now the third condition is the most delicate. Nice Markov chains are what's called positive recurrent. And what that means is the following 2 things. For all states I, if the process starts at I, it will return eventually to that same state with probability 1. That's another mixing kind of idea. It wants to go away, but it also wants to come back. And part B, not only that, but here's the tricky part. The expected length of waiting time until it first gets back has to be finite for it to be positive recurrent. And you can imagine Markov chains where the thing wanders off to infinity, really far toward infinity, and then does come back. And it turns out that how long you expect it to wait for it to come back is not finite. And so like I'm saying here at the bottom of this page, this is quite delicate. Wherever the chain is now, we insist that it must certainly come back here, but we don't expect to have to wait forever for this to happen. That's what positive recurrence means. Now, my Markov chain a minute ago, my random walk, is definitely irreducible, because if you think about that random walk I defined, no matter where it starts, the chain can reach any other integer in a finite number of steps with positive probability. That's true. And it's also aperiodic because I allowed it to stay where it is. But unfortunately, it's not necessarily positive recurrent. It will depend upon those numbers P1, P2, and P3. And the problem is the second part of the positive recurrence part, the part B. It's true that this chain has positive probability of returning to wherever it started, but because capital S consisted of all integers going out to minus infinity and out to plus infinity, because it's unbounded, this probability may not be 1. And on average, you may have to wait forever for it to return. So this random walk is not positive recurrent, and that means it won't necessarily have the kind of nice behavior that we're going to try to have it have in order for it to be useful to solve the Bayesian integration problem. So what simple thing could I do to the state space to force it to be positive recurrent? The problem was that it was allowed to wander off toward infinity, and so the obvious thing to do is to do what? Bound it. And so I can fix this by bounding S. Suppose instead that S consists of the integers from minus k to plus k for some number k. And I keep the same transition probabilities as before, except I reject any moves that attempt to go outside the boundaries. So once it's at plus k, since the move rule says it could either go back 1 or stay there or go 1 more, it might sometimes try to go 1 more, and my rule is every time it tries to do that, I just say no to it, and it loses a turn, and then it has to try again. So that's my rule. Now, everything's great. Now, it's still, of course, it's still aperiodic, and it's clearly still irreducible, sort of even better somehow. And now it's positive recurrent because everything is finite, nothing bad can happen. So this bounded random walk now satisfies all 3 of the nice properties. So having told you which are the nice Markov chains, I next have to tell you what it is that you get for those properties that makes them nice. And it seems that we're ready for our next break. So I'll do that when we start again at 11:30. So now we have a nice Markov chain. And you can think in this example of the bounded random walk that I just developed. Imagine running this chain for a long time and paying attention to the relative frequency with which it visits all the states that are available to it. What do you think would happen if the chain were nice eventually? You'd cover all the state space, but moreover, because of those three carefully chosen properties that govern niceness, the relative frequency distribution of how often it visits the states should settle down into something that approaches a kind of regularity. Any given move will be random, but if you keep track cumulatively over time of where it's been, you can hope that that will settle down into something that's quite stable. And so that's what turns out to happen. So imagine running the bounded random walk for a long time, and it doesn't matter very much where you start, it's going to turn out. So start somewhere, and then run it for a long time. Look at the distribution of the states that it's visited so far. Over time, this distribution should settle down or converge to a kind of limiting steady state behavior. And I can demonstrate this to you by simulation. So I've written a little function that simulates this bounded random walk. So this function is called rw.sim, randomwalk.sim. And it takes as its inputs, first of all, k, and that tells us how big the state space is from minus k to plus k. P is a vector of those three numbers, P1, P2, P3. Theta.start is where it's going to start. I'm thinking of theta as taking on possible values from minus k to plus k. N.sim is how many times I want it to actually simulate from that starting value. And the seed is, as usual, where I start things to get replicability for random functions that produce random output. And so this function starts out by setting the seed, and it sets theta to be equal to what you get by repeating 0, n.sim plus 1 times. So that's a vector of all zeros of length n.sim plus 1. And that represents all the places that it has visited so far. And the answer is it's not visited anywhere yet. And it starts off at theta dot start. And so I load in theta dot start into the first position in this vector theta. And then as I runs from 1 to n.sim, I generate theta I plus 1 by making a move. And that's another function I've written that's indexed by k and p and where I am now. That's the Markovian part. And then when I'm done, I simply return a frequency table of the values that theta has achieved. And the move function looks like this. It's simply, well, it's a little more technical, but you can see what it does is it samples going left or staying where it is or going right with probability P1, P2, P3, and then it tries to make that move, and as long as that move is within minus k to plus k, it accepts that move, otherwise it tries again until it does get a move that is accepted. So let me go back to the course web page. You will find that there's also some code down here at the bottom for simulating from this random walk. So I'm going to go ahead and copy this into R and load up some values. Let's start with a random walk that is equally happy to go either left or right or stay where it is. So my probabilities, my transition probabilities are a third, a third, a third. And let's say we're doing this on the state space of the integers from minus 5 to plus 5. And let's say we start things off at 0. And we use the same, perhaps, random number seed I used before and run the random walk for 10 iterations and see where it goes. So I'll start over again with a blank copy of the R workspace using that command I showed you before. Remove, RM for remove, list equals ls, open parenthesis, close parenthesis, close parenthesis. That says make a list of all the objects that are in here now, and then pass that list to remove, and so it removes all the objects. And now if I hit this with Control V, it reads all that stuff in and comes back and says, okay, In the first 10 iterations, starting at 0 with that particular random number seed, it's only managed to go a little bit to the left, never to the right so far with that particular random number seed, and it's visited those 3 places 3, 4, and 4 times. That adds up to 11 because I loaded in a 0 right at time 0. So that's not very interesting. We haven't learned much yet. Certainly don't see any steady state behavior yet, but let's run it 100 for 100 time periods and see what we get. Now it's managed to make it from all the way down to -5 and all the way up to +3, but I still don't see any regularity emerging in the frequencies. Now let me run it for 1,000 and see. Now it's managed to make it all the way from -5 to +5, and you might believe there was some regularity there, but I certainly don't see any kind of monotone pattern or any kind of things settling down into things. What would you expect? Tell me what you expect the limiting behavior to be for this chain. If it's completely happy, just as happy to go left or stay where it is or go right, then what's it going to do? It's going to be uniform, except at the very end points, because I have that funny thing happening where I reject moves that are outside. So all the way from -4 to +4, it's supposed to be uniform, right? It's just got to be, unless there's something wrong. And then at -5 and +5, it won't end up there as much because of the way I set up that rejection rule. Well, let's try it again. Let's give it 10,000 iterations now. And now you begin to see the regularity you guys said. The frequencies from -4 to +4 are all kind of close to each other. It's starting to show the uniformity that you expected. And notice the -5 and the +5 don't occur as often as the -4 to +4. So let's try 100,000. And that only took 2 or 3 seconds. And now the regularity from -4 to +4 is becoming even more evident. And the -5 and the +5 are coming out about as often as they each other. And that's as it has to be as well by uniformity of the P1, P2, and P3. Yeah, I probably should have wrapped. Whenever it tried to move from, that would have given complete uniformity if I'd wrapped it. But this is an interesting thing to look at also. When it gets to +5 and it tries to move to +6, I just send it down to -5. That would have been a different way for the chain to behave at the edges. But this is fine. So now let me give it 1,000,000 and see how long it takes. It took 2 or 3 seconds to do 100,000, so maybe it'll take about 20 seconds to do 1,000,000. Let's see. One second, I'm going to time it. Only took 16 seconds. With a different seed, if everything's working great, how should the numbers with a different seed look in relation to these tables here? It should look almost the same. The seed is just giving us one particular choice of pseudo-uniform random numbers or another one. And so, yes. Yes, and there are other seeds that might initially head to the right and so on. But notice how it didn't matter in the long run whether it initially headed to the left or not. So what's happening here is that actually no, that's true. This is a markup chain that where it's been in the first 100 places depends a little bit upon the random number seed, for example. But by the time you get to where it's been the first 1,000,000, it doesn't matter at all. That's right. And the edges are 2/3 of the middle. That's right, which makes sense if you think about it. Because I'm throwing away 1 out of the 3 possibilities, so no surprise. Okay, so it's doing what we would expect. The -5 and the +5 have to have the same probability, and it's about 2/3 of the other. And all the other ones are numbers that are all the same by that symmetry in the P1, P2, and P3. Cool. So there it is. Having set up a markup chain to have nice behavior, the reward of having nice behavior is that it has a long-run behavior that's stable. People call the limiting distribution the equilibrium distribution is one name for it. A stationary distribution is another name for it. So, okay, we've just run the code here, and now you have seen what the result is. So the distribution of where the chain has visited is converging to something close to uniform on -5 to +5, except for the effect of the boundaries. So let's let Q1 be the limiting probability of being in one of those 9 non-boundary states from -4 to +4. Let's let Q2 be the long-run probability of being in one of the boundary states. And if you just think through the symmetry argument, you can guess that Q1 and Q2 should satisfy 9Q1 plus 2Q2 has to add up to 1. And Q1 has to be 1.5 times as big as Q2. And then you solve and you get 3 over 31 for the states in the middle and 2 over 31 for the states on the edges. And so now I can take all the numbers I just showed you, and based on that run of 1 million, a million plus 1 iterations, I could estimate those probabilities empirically as about 0.0968 and about 0.0644. And the right answers are 0.0968 and 0.0645, so pretty good. The limiting distribution does not depend on the initial value of the chain. Let's try that. Let's play that game. So let's go back here, and I'll go back to the very first one that had that one there. And instead of starting it off at 0, I'll start it off at plus 5, just to have something else to do. So at the beginning, it's very different, of course. But watch as I give it 100, and then I give it 1,000. Whoops, come back, little Sheba. Give it 1,000. It's begun already to shrug off the dependence on the initial state. By the time we get to 10,000, you can hardly see, that's hardly different from what I showed you before with that different initial state. Now out to 100,000, pretty fast, and also uniform closely, except for the endpoints, and 1 million about another 15 seconds. So it shouldn't depend on where it starts. It should shrug off any temporary dependence on its initial state. It should have a long-run equilibrium stationary distribution. That distribution should be determinable completely from P1, P2, and P3. Do you buy that? Because that's exactly what governs this Markov chain, was that vector of transition probabilities. And it shouldn't matter what the seed is either. I could rerun this with lots of different random number seeds, and the story at 1 million would be almost the same, just Monte Carlo noise. Now, of course, you get different limiting distribution with different choices of P1, P2, and P3. Suppose I set things up so that it only had 20% chance of moving left, 30% chance of staying where it is, and 50% chance of going to the right. Then what do you expect the equilibrium distribution to look like now? It has a powerful desire to move to the right. Therefore, the equilibrium distribution is going to look like a triangle, right? It's going to have its highest frequency at plus 5 and monotonically smaller from that point on. Well, let's try it. So I'll fire up. I'll pick off this vector of P and start it up at 0 and see what happens. Now I'll give it 100. And look, it's already trying to move to the right with 100. And I'll give it 1,000. And now it's already pretty close to monotone with 1,000. At 10,000, it is in fact totally monotone. And you can see what's happening. It's just doing what you expect. So just as you would expect. And again, we could derive the limiting probabilities from the vector of P if we felt like it. Okay. Now some more names for what's happening here. A positive recurrent and aperiodic chain has a name. It's called an ergodic Markov chain. And it turns out that such chains automatically possess, not only do they possess a stationary or equilibrium or long run or invariant distribution on the possible states, which we could call pi as a distribution across those states. Not only does it possess such a thing, but that particular long-run distribution is unique. And it's characterized by the relation that you see there in equation 12. For all states j and all times t greater than or equal to 0, where Pij of t is the transition matrix of the chain, it's the conditional probability of being in state j at time t, given that you were in state I at time t minus 1. those of you who are mathy might recognize what's happening with that equation 12. If I wrote it in vector and matrix form for you, it would read pi equals pi p. Does that ring any bells in linear algebra? It's an eigenvector. So pi is a left eigenvector of the, in other words, the stationary distribution is a left eigenvector of the transition matrix. And you can use that fact to solve for what the stationary distribution is. Informally, we don't need to go there. Informally, the stationary distribution characterizes the behavior that the Markov chain will settle into after it's been run for a long time, regardless of its initial state. So now we're in a position to think about how Metropolis and his colleagues would have applied this. Given a parameter vector theta and a data vector y, the Metropolis et al. Idea is to simulate random draws from the posterior distribution p of theta given y by constructing a Markov chain that has p of theta given y as its stationary distribution. If you could build a Markov chain that had the target distribution as its stationary distribution, then you could start it anywhere you like and let it run for a while until it has reached equilibrium and throw away all those initial draws that you had to wait through till you got to equilibrium, and then just run the Markov chain for a long time, monitor the Markov chain for a long time after that, saving all of those draws into a data set that I'll call the Markov chain Monte Carlo, or MCMC data set, and then analyze that data set the same way we did earlier, as if it were an MC data set. You got columns and numbers. If you want to know what the posterior mean is in a particular element of the parameter vector, you take the mean of those numbers there, and so on. So the Markov chain has to have the following four properties. First of all, it should have the same state space as theta does, because you want where the outcome of the Markov chain to land to be corresponding to all the different places that theta could be. That seems reasonable. Secondly, it should be easy to simulate from. That's going to be important. Thirdly, and most importantly, its equilibrium distribution should be the thing that we care about. And then there's another technical condition that we would very much like to have. And let me tell you what that is and remind you why we would want that. So you may recall that when theta is a vector, so now theta is of length k, Bayes' theorem said that the posterior for theta, given the data vector and the background information, is equal to the prior distribution times the likelihood distribution. But you will recall that when we use Bayes' theorem in on a vector of length greater than 1, this thing is a k-dimensional distribution, this thing is a k-dimensional distribution, and this thing is a k-dimensional distribution. And so, by definition, this normalizing constant is going to be hard to compute. Because to do so, we'd have to do a k-dimensional integral. And the whole point of the MCMC approach, the Metropolis algorithm, is to avoid doing all of the integrations that arise in Bayesian work. All of them, including that one there. And so, wouldn't it be nice if we could achieve all three of those things I've already said are desirable goals, while at the same time being able to work not directly with the density that's been normalized, but with any unnormalized version of it? Wouldn't that be nice? Because then you wouldn't have to compute the normalizing constant. So if it were possible to achieve those three goals I've stated here already in such a way that you don't need to have previously normalized the density that we're trying to sample from, that would be really brilliant. Because then the integral, the k-dimensional integral that we would have to compute to work out the normalizing constant would not be necessary. And so the final requirement is it would be great if you don't need to know the normalizing constant for the posterior distribution when building the chain. And the way the fourth thing turns out is very beautiful. Pardon? Oh, I'm sorry, yeah. In fact, we already have a hint of why it's going to come out nicely, because the Metropolis approach builds on Mr. von Neumann's rejection sampling. And how did we decide about the acceptance probability in rejection sampling? We took a ratio of the height of the target distribution, the height of the target distribution at the particular point, divided by the height of the envelope function at that particular point. If we can somehow set things up so that the envelope function is the target distribution at a different point, then we'll be evaluating a ratio of the target distribution at two different points, and what will happen to the normalizing constant? It'll cancel, right? If I'm able to somehow set the algorithm up so that the acceptance probability is driven by the height of the target at one point divided by the height of the target at another point, then it doesn't matter whether it's normalized or not, because whatever constant you would have had in there would have canceled anyway. Unbelievably clever. The way to do this turns out to be very simple, and yet to prove that it works is actually quite complicated. And I am imagining, I'm sure it didn't go this way, but I'm imagining that they sat around for a long time trying to figure out how to do it, and then finally one of them said, I'll give my soul to the devil if they show me how to do this. And right away the devil pops up in the room and says, is that really what you want? Here's a piece of paper, I need you to sign it. And maybe it was Metropolis, maybe it was probably Edward Teller, wasn't it? So Edward Teller says, yes, I'm going to hell anyway for what I've done with the hydrogen bomb and so on. So yes, I'll sign the paper. And now the devil shows them, and it's so simple that Teller is pulling his hair out because he can't believe that he just gave his soul away for something so simple. Well, here we go. That's what we're trying for. If you can do this, then you can run the Markov chain for a long time, as I said before, starting from anywhere you like, running it for a while until it's reached equilibrium, and tossing away that stuff that you didn't really care about while it was finding equilibrium. And then, once it's gotten to equilibrium, generate a huge sample of draws from the posterior distribution, and then just use simple descriptive summaries like we talked about before. Sample means, sample standard deviations, sample correlations, sample histograms, or sample kernel density estimates to extract any features of the posterior that you want. Tremendously cool idea. And the mathematics that underpins this is something called the ergodic theorem, which says formally that if the Markov chain theta t star is ergodic, and little f is any real valued function for which the expectation of the absolute value of f of theta is finite, then with probability 1, as the number of monitoring iterations goes to infinity, the sample average of f evaluated at the Monte Carlo points will converge to the actual expectation of f. And in plain English, that just means simply that as long as the stationary distribution is the target, you can learn to arbitrary accuracy about anything you want, like posterior means, standard deviations, and so on, just by waiting for stationarity to kick in and then monitoring thereafter for a long enough period. The ergodic theorem is a version of the weak law of large numbers. Now, it's a nice theorem. Theorems are nice, but they often are nice only up to a point, and the point that they're nice only up to is that the theorem is silent on how big little m has to be in order for everything to work well. So, in fact, there are two things that it's silent about. It's silent about how long you have to wait in terms of number of iterations from a given starting point to get to stationarity, and then how long to monitor after that. And a third practical issue, of course, is what to use for the initial values. You have to start the chain somewhere. Intuitively, the closer the starting value is to the center of the posterior, the less time you should have to wait for stationarity. But that's a little circular, isn't it? Because if you don't know the posterior, you won't know where its center is. And so how do you know where to start the chain? Well, sometimes you can do things like the following. One of my PhD students when I was in England, Bill Brown, and I are the co-developers of the MCMC capability in a widely used package for hierarchical and multi-level modeling in the social sciences called MLWin. And the ML part of MLWin is maximum likelihood. And so inside this package, there were routines already written by somebody else that computed the maximum likelihood estimates in quite complicated hierarchical models. So that was wonderful for Bill and me because we could use the maximum likelihood estimates as starting values for the MCMC. By definition, they ought to be pretty close to the posterior mean with diffuse prior information, and so why not start there? So we were lucky inside MLWin, but in general, you won't necessarily be quite that lucky. But it's going to turn out that you can even use generic starting values that might be quite far from the actual posterior mean, and the chain is going to shrug that off very quickly. The time to achieve stationarity is going to turn out to be really small. Now, the standard way to deal with waiting for stationarity is to do two things. Run the chain from a good starting value, theta 0 star, let's call it, for lowercase b iterations until equilibrium has been reached, and then discard this initial period, which is called the burn-in period, after something that maybe there isn't anybody in the room who's ever experienced. But in the old days, when you were doing electronical engineering experiments or physics experiments with oscilloscopes, you would come in after having been at your home overnight, you'd come in the morning and turn the oscilloscope on, and you could not dare to take any observations right away until it had burned in, until it had settled in. The old oscilloscopes had vacuum tubes in them, and you had to wait for the vacuum tubes to get over the initial surge of electricity in them and things like that. That was called by the oscilloscope people the burn-in period, and we use the same name here in MCMC. So we have to wait for the oscilloscope to reach stationary behavior before using it. We have to wait for the Markov chain to achieve stationary behavior before using it. So we wait for little b iterations and then discard this initial burn-in period completely like the oscilloscope people do, but that doesn't say how big that number little b should be. So as soon as people started seeing that this was a good way to approximate Bayesian integrals, a little cottage industry of new problems emerged. So our first order problem is how to approximate the integrals, and this is going to solve that problem, it turns out. But now we have a small set of second order problems, namely these questions here. Basically, they are questions having to do with the topic of MCMC diagnostics. Where should I start the chain? How do I know when I've reached equilibrium, which is like asking how big that number little b, the length of the burn-in period, should be. And once I've reached equilibrium, how big should the monitoring run be? In other words, how long should I monitor the chain to get whatever accuracy I want? Now, something about this should perhaps be bothering you. What I said was we're going to get this data set, the MCMC data set. We're going to start somewhere. We're going to burn in for a while until we think we're at equilibrium. Then we're going to throw all that stuff away, and then we're just going to monitor from that point on. But the numbers in any column of this data set, which are the monitored values for some particular parameter in the vector, they're no longer IID. They are the output of a Markov chain. And they're the output of a Markov chain that in some cases remembers quite a lot about where it was a moment ago. In fact, it has to know where it is now to know where it's going to go next. And so if you thought of the column of the MCMC data set for a particular parameter as like a time series where time was iterations again, you would find that that time series does have a lot of memory. It remembers where it used to be. In other words, we do, it turns out, have the identical distribution property, which we agreed was vital to this whole thing, but we don't have independence anymore in these draws. And here I was a minute ago saying to you, all you need to do is calculate the sample mean of the numbers in the monitoring data set in any given column, and that will be your Monte Carlo estimate of the posterior mean for that quantity. But does that work for time series? Because the draws are not independent. They may be highly positively correlated with each other, and they often will be. And yet there's this cool thing, this is a fact from time series that says as long as the time series is stationary, the sample mean of a bunch of draws from it is a good estimate of the underlying mean of the process, of the stationary distribution that the time series is expressing. And so on for any other function of the underlying target distribution you're interested in. So the Monte Carlo, this is a little bit about both the Monte Carlo and MCMC data sets, and here's how it goes. The basis of the Monte Carlo approach to obtaining numerical approximations to posterior summaries, like means and SDs, is the weak law of large numbers, which just says that with IID sampling, the Monte Carlo estimates of the true summaries can be made arbitrarily close to the truth with arbitrarily high probability as the number of monitoring iterations gets really big. And the fancy name for that is that those estimates are consistent. It's a frequentist idea, meaning just what I said. They can be made arbitrarily close to the right answer with arbitrarily high probability just by having a lot of numbers going into the means and so on. But before I get to that business about how stationarity, or rather how the non-independence of things affects things, let's look at quite concretely how it being an MCMC data set would change things. So let's look at the practical consequences of switching from IID sampling to Markovian sampling. So if I were to run that IID rejection sampler that I told you about before on that Berkeley proportion of bicycle traffic example earlier, for a total of little m monitoring iterations, the result would be something that I have called the Monte Carlo data set. It would have one row for each iteration and one column for each quantity that I monitored. And in that particular example, it might look like this, and the Monte Carlo standard errors are given in parentheses here. So I have a table that starts out, the first column is iteration number, the second column is the sampled values of theta, and the third column is the sampled values of the indicator function that theta is less than or equal to 0.15. So the iterations run from 1 to little m, which was 31,200. And the theta stars bounce all over the place because they're IID draws from that beta distribution. So the first one might come out 0.244 and the next one 0.137 and so on. And the indicator function for whether that number was less than or equal to 0.15 is just a bunch of ones and zeros, and you can answer it deterministically by looking at the theta star in that row and seeing if it's less than or equal to 1.5 or not. So you get a bunch of ones and zeros over there. Now take the mean of the theta column and the mean of the indicator function column and work out the Monte Carlo standard errors. Also, while you're at it, take the standard deviation of the theta column and make a density trace of the numbers in the theta star column. So everything you want to know is right there in that MC data set with some simple descriptive summaries applied to the columns. Now, running the Metropolis sampler on the same example would produce something a bit different. It would give you something that might be called the MCMC data set. It would have a similar structure as far as the columns go, but the rows would be divided into three phases. Iteration 0 would be the initialization phase where we start the markup chain somewhere. Iterations 1 through B would be the burn-in period during which we're waiting for the chain to reach equilibrium. And iterations B plus 1 down to B plus M would be the monitoring run on which the real summaries of the posterior are going to be based. And so the MCMC data set would now look like this slightly more complicated table. I have iteration number on the left and which phase of the sampling that corresponds to, and then the theta star column and then the indicator column. So I started off at iteration 0 at some place. Here I started it off at 0.200. Then I burn in for 500 iterations, let's say, and the theta stars bounce around from that initial value. And then I draw a line right there, and I throw away all those first 501 iterations altogether because they were part of the process where we hadn't reached equilibrium yet. And then from iteration 501 to 31,700 all the way out to B plus 1 to B plus M for 31,200 monitoring iterations, I continue to let the chain run and get those theta stars from B plus 1 down to B plus M and also the I stars. And now I do the same things as before. I make descriptive summaries of the theta column and descriptive summaries of the indicator column. However, how are things going to be different? If I were able to do an IID sample from this particular distribution, and you could only do one of these MCMC samples, how would they be different? Well, if everything is going well, would we get approximately the same thing for our estimated posterior mean of theta? Yes, right? Because we're just using two Monte Carlo valid ways to learn about something. Would we get about the same thing for our Monte Carlo estimate of the posterior standard deviation of theta? Again, yes. Would we get about the same thing for our Monte Carlo estimate of what the density, the posterior density looks like for theta? Again, yes. So it's seeming as though there wouldn't be any differences at all between these tables. But look, if I only had 31,200 monitoring iterations in this table here, and I had the same number of monitoring iterations in the other table, that does turn out to create something that's different, as follows. Because the draws in the MCMC data set are correlated with each other in time. In other words, if I look at theta star B plus 1 down to theta star B plus M, and I imagine that as a time series of values, and I ask how it behaves, it will not behave like white noise because I generated it as draws from a Markov chain. And in fact, if you think about what's going to happen, because the Markov chain depends on where it is now to decide where to go next, which is something that the IID story does not do at all, there's going to be a relationship between the next theta and the one you're at now. The next theta is somehow going to be similar to where you are now because you used where you are now to decide where to move to next. Does that make sense? So theta star b plus 2 should be related to theta star b plus 1 because of the Markovian character, and in such a way that they ought to be fairly close to each other. And so when one of them is big, the other one will be big, and when one is small, the other one will be small. Therefore, this time series is going to exhibit a kind of correlation with itself in time. Can you imagine that? It's called, in the time series business, it's called autocorrelation. The time series will be positively autocorrelated, meaning that it has a memory of where it was a moment ago, and that memory borrows from what we just were, where we just were. And what that means in practice is that every time we get some new data from the Markov chain, we get some new information, but we get a rehash of old information at the same time. So what's the net of all of that? Would you expect the IID Monte Carlo sampling to be more or less accurate than the MCMC sampling? Which one would be more accurate, the IID sampling or the MCMC sampling? The IID sampling would be more Monte Carlo accurate, and that will show up in the Monte Carlo standard errors being smaller for the IID version than for the MCMC version. So notice how in this table the 0.2177 estimated posterior mean for theta has a Monte Carlo standard error of 0.009, and down here in this table the Monte Carlo standard error is, where did it go? I'm going the wrong way, sorry. Oh, okay. The MCMC standard error was 0.009, and the Monte Carlo standard error was 3 times smaller, 0.003. And so essentially what turns out to be true is that the fact that we are sampling from a time series does not affect the validity of our sampling algorithm at all. It's just as Monte Carlo valid as if we had been able to choose an IID sampler, which will be difficult to do in high dimensions. But they're equally Monte Carlo valid, but the IID story would be more Monte Carlo accurate, and sometimes substantially more Monte Carlo accurate. So in other words, to get the same accuracy from MCMC as you would have been able to get from any fixed set of iterations with IID, you're going to have to run the MCMC sampler, what, longer or shorter than the IID? Obviously longer. And the question is going to be how much longer? Is it going to be 10 times longer? Is it going to be 100 times longer? Is it going to be 1,000 times longer? What's it going to be? And I've certainly worked with chains where the answer was it needs to be 10,000 times longer in order to overcome all the serial dependence in the data. But look how we're going to overcome that. We're just going to use, what's the name of that rule? Moore's law, is it, about how fast CPUs get faster? We're just going to let Moore's law help us. Yes, it's going to take 1,000,000 iterations instead of only 100 or 10,000 or 1,000 or whatever. But 1,000,000 iterations only takes a minute and a half, whereas the 1,000 iterations was the blink of an eye. And I don't care. Minute and a half, I'll go read my email, or I'll go get a cup of coffee, or even if it's not a minute and a half, it's 45 minutes. I'll go to lunch or something like that. So we're going to overcome the inherent Monte Carlo inefficiency of MCMC simply by having fast computers and letting them run for a while. Yes, please. It's not only, it's not exactly expensive, because if you can figure out how to do it, it's actually Monte Carlo cheaper than this thing here, because you're getting more information per iteration this way than you would with the MCMC story. The problem is that in high dimensions, you can't find an envelope function. So you just can't do rejection sampling in high dimensions. So that's why Metropolis and his colleagues invented a variant on rejection sampling that does work. In effect, it creates something like the envelope. It creates an adaptive envelope function. That's what it does. No, it's that you literally can't find you cannot find an envelope that you can prove mathematically really is an envelope. The worry is that no matter how high you try to make it, there might be some place way out in the tails where it actually crosses below the actual target, and then you're going to get the wrong sampling probabilities. So it's hard to build envelope functions that are reliably true envelopes in high dimensions, and you can try it for yourself. It's just people have a lot of experience trying to do it, and it's just hard. Okay. Yes, please. Well, the only if part of if things are going well is if we are able to construct a Markov chain that has the target distribution as its stationary distribution. So first of all, the Markov chain has to have a stationary distribution, and we're going to restrict ourselves only to ones that do, only the nice ones. And secondly, we have to ensure that the Markov chain has the stationary distribution we want. That's actually an order of magnitude harder than going the other way. If I gave you a Markov chain and asked you what its stationary distribution was, it's not very hard. You build the transition matrix and you take the left eigenvectors and you look at them. But if instead I ran things in the other direction, I told you I wanted a Markov chain that had blah blah as its stationary distribution. That's much harder because you have to reverse engineer the whole process. That's where the real cleverness came in them figuring out the Metropolis algorithm. Any of us in the room could work out an equilibrium distribution if were given a transition matrix. It's just linear algebra, but going the other way is actually much harder. So thinking of iteration number I in the Monte Carlo sampling process as a discrete index of time, t, so that the columns of the Monte Carlo and Monte Carlo MCMC datasets can be viewed as time series, I need to bring in an important concept from time series for you. It's a thing I mentioned a minute ago. It's called autocorrelation. The autocorrelation, we'll call it rho sub k, of a stationary time series, theta star t, at what's called lag k, is simply the ratio of the covariance of the series at time t with itself, t periods backwards into the past, divided by the variance of the series. In other words, that's how we compute correlations. We take covariances over variances, actually, when you're doing it with itself. So here's what I want you to imagine. Here's the monitoring part of one of these MCMC data sets. And here's the column for theta. And here's, I'll reset the clock. So this one is theta star 1, and where 1 really means having started the clock over after all these iterations up here that we threw away. And here's theta star 2, and dot, 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 down to theta star m. Yes, please. To measure how correlated the time series is with itself, imagine taking this same thing and shifting it one iteration. So now we're seeing how closely theta 1 star relates to theta 2 star, how closely theta 2 star relates to theta 3 star, and all the way down to, we would try for theta star m plus 1, but there isn't one down there, so we throw that row away. Now, I ask you to take these two numbers and just feed them into R and calculate the ordinary sample correlation between those two columns. That represents how strongly correlated the time series is with itself one period backward in the past. That's called the first order autocorrelation, rho 1. And we would like that number, if we had white noise, what would that autocorrelation be? 0. We would like that number to be close to 0. And in fact, with many MCMC samplers, the problem is that with MCMC, you get rho 1s on the order of plus 0.8, plus 0.9, plus 0.95. You get some really nasty numbers. So the series is hardly learning anything new each time, but it's learning a little bit new each time. And we simply overcome the inefficiency that arises from this by just sledgehammering it. We just run the chain a long time. That's going to be our goal. Now, if you wanted to be clever, it's going to turn out that just as it was the case with von Neumann's approach, in which there were many different possible envelope functions, it's going to turn out that there are many different normalized envelope functions, which were called proposal distributions in the MCMC story. Many different proposal distributions, and you can try to be clever and find a better proposal distribution, which would be one that would generate a smaller value of rho 1, a value of rho 1 closer to 0. And there's been a very active literature in the past 20 years trying to figure out how to make Markov chains more clever, MCMC more clever, by creating Markov chains that have a lower degree of positive autocorrelation in the output. But it's a hard problem, and we're not going to go there here. We're just going to use standard code like JAGs. I'm going to show you guys next time, all the Mac people in the room, I'm going to show you how to use JAGs next time, because it turns out to build directly off of WinBugs. And so we're going to look at WinBugs today, and then I'll show you JAGs next time so that you guys can, all the Mac people in the room can do it as well. We're just going to use the built-in proposal distributions inside these pieces of freeware because it's a tremendous pain in the butt to figure out better proposal distributions than someone else's. It's really hard work. So we're going to default that to these software packages and then just overcome the problem by running the chain a long time. So these autocorrelations measure the degree to which the time series at any given moment depends on its past history. We want them to be close to 0, but they're often not. So as we just said, IID draws from the Pasteur correspond to white noise. That's a time series with 0 autocorrelations. And now I should tell you what is meant by this thing about lags. So this is the, oops, I see. I forgot to move over again. This is the autocorrelation row 1 at lag 1. Actually, it would be row 1 hat. We'd estimate it from the data. To get the one for lag 2, you simply take the correlation of theta star at time 1 with theta star at time 3, then the one and so on. 2 goes with 4 and dot, dot, dot down. Theta m goes with theta m plus 2, and you end up having to drop off the last 2 rows of the data set. And now you take the correlation between this column and this column. That represents what people call row 2 hat, the autocorrelation at lag 2, for example. You can do that. You can play that game with further lags. By the way, if the time series is stationary, does it matter whether you think about running time backwards or forwards? If it's stationary, and I think about running the time series forward in time, and you think about running it backwards in time, we should get the same basic stochastic behavior because it's stationary, right? And so when I talk about going back forward in lags, I could talk about going backwards as well, and we should get the same kind of thing. So like it says there on the top of this page of the organized notes, IID draws from the Pasteur correspond to what the time series people call white noise, namely a time series with 0 autocorrelations at all lags. And this is the behavior of the columns of the Monte Carlo data set from IID sampling that is produced by ordinary rejection sampling. But as I mentioned a minute ago, because of the Markov character of the columns of the MCMC data set that we looked at before, the MCMC data set, each column, when considered as a time series, will typically have non-zero autocorrelations. And because Markov chains use their present values to decide where to go next, it wouldn't surprise any of us to hear that the typical behavior will be positive autocorrelations, and in fact, often substantial positive autocorrelations. And it's for the reason I mentioned intuitively a moment ago. Every time you get another draw from a Markov chain, you get some new information, but you get a rehash also of old information. And so the new draw is going to be related to the old one, therefore positively correlated with it. And it's a marvelous result from time series analysis. The ergodic theorem is a generalization of the ordinary weak law of large numbers for IID quantities. It's a marvelous result from time series analysis that all of our usual descriptive summaries of the Pasteur are still consistent as long as the columns of the MCMC dataset form stationary time series whose equilibrium distribution is the Pasteur we're trying to sample from. And remember, the word consistent means just that idea of you can get as close to the right answer as you want by simply getting a lot of more and more and more monitoring draws. So in other words, provided that you can achieve those 4 goals that I mentioned earlier that Metropolis and his colleagues set for themselves, and provided that you only do your monitoring after the Markov chain has reached equilibrium, then the MCMC approach and the IID Monte Carlo approach will both be equally Monte Carlo valid. They will both get the right answers. But they may well differ on their efficiency, by which I mean the rate per iteration or the rate per CPU second at which we learn about the Pasteur distribution with those 2 different methods. That efficiency may not be the same, and it will generally be the case that the MCMC approach has lower Monte Carlo efficiency than the IID approach, the Monte Carlo approach. And so we're going to end up with slower learning, namely larger Monte Carlo standard errors than with IID sampling, and we're going to overcome that just by brute force, just by running the sampler for a long time. Yes, you can. The standard software will plot. If I draw the autocorrelations as a little function where in the horizontal scale, I keep track of how many lags I am away from any given reference point. And the vertical scale is how high the autocorrelations are. That's called the autocorrelation function. And WinBugs and the other basic routines all plot the autocorrelation function for you, and you can see just how bad the Monte Carlo inefficiency is from that. And that, in turn, also the software will have Monte Carlo standard errors in it, and you can see how big they are. And either use some formulas that I'm about to show you later on today, or else just do it by trial and error. Look at the Monte Carlo standard error. If it's small enough, then you don't have to have any more iterations than that. And if it's still bigger than you want, then go ahead and toss in another 100,000 iterations and look at the Monte Carlo standard error again, and keep doing that until it's as small as you want it to be. So we are going to be able to overcome this. These packages will have the information we need to be able to get the Monte Carlo accuracy we need. Did that help answer your question? In fact, the way it's going to work is the usual square root law, namely to cut my Monte Carlo standard error in half. It's not enough just to double the length of the monitoring run. I have to quadruple it. Remember, that's how uncertainty works for means in general and for most parameters that are like means. It's just that, so it is going to be true even with MCMC, that if I want to cut the MCMC Monte Carlo standard error in half, I have to quadruple the sample size. It's just that the MCSE, the one from MCMC, is going to be bigger than you would have liked just because you're using Markov chain Monte Carlo rather than IID sampling. Now, now we get to the point where I get to tell you what the algorithm is. And it's, I hope you'll agree with me that it is pretty cool. So here's how it goes. Actually, I want to warm us up for it with a few more sentences from the organized material here. They were able to create, Metropolis and his colleagues, including Edward Teller, were able to create what people would now call a successful MCMC algorithm by the following line of reasoning. And as I said, you can read more from that book by Wally Jokes and others to learn more about this. And that could include just reading the chapters that I posted on our webpage. So consider, we start with von Neumann. Consider that rejection sampling method given above in the box that was equation 8. So let's go all the way back there and look at that box again. So there's, oops, there's von Neumann. You have a target density P of theta given Y. You have an envelope function G, which has to be integrable. In other words, its integral has to be finite. And when you do integrate it and divide through by its integral, that will normalize it so that its integral is 1. That will make it a proper probability distribution. Call the normalized version of the envelope function lowercase g. We're going to call that thing the proposal distribution. And define the acceptance probability in the way that von Neumann is suggesting, and then you have a little teeny algorithm like you see right there that's codable up in only 8 lines of pseudocode. So that's von Neumann. What Metropolis et al. Were able to do was something very clever. You'll notice that in von Neumann's algorithm, the proposal distribution, the normalized version of the envelope, always stays the same. For every single draw, you use the same exact envelope function and therefore the same exact proposal distribution. What Metropolis and his colleagues said was, in order to avoid the problem of not being able to find the envelope function in high dimensions, we're going to go ahead and use this Markov thing, and we're going to do it by allowing the proposal distribution to change from iteration to iteration. In other words, we're going to make the proposal distribution be adaptive in a certain sense. And that's going to give them the freedom that they needed to not have to worry about that envelope function. So let's think once again about the rejection sampling method, regarding it as a mechanism for generating realizations of a time series, whereas as before, time index is just iteration number. And so here's von Neumann again with ordinary rejection sampling. At any time t in the process, you make a draw theta star from the proposal distribution, lowercase g of theta given y, which is just the normalized version of the envelope function, capital G, and you either accept what we will call a move to theta star, so you actually move the chain so that the value at time t plus 1 is this new theta star, or you reject it according to the acceptance probability, which is computed by the ratio of the height of the target at where you're thinking of going divided by the height of the envelope at where you're thinking of going. And for von Neumann, if you accept the move, the process then moves to theta star. If not, you draw again and discard all of the rejected draws until you do make a successful move. So that's words that describe von Neumann's story. So, as I mentioned before, the stochastic process generated in this way is an IID or white noise series of draws from the target. Metropolis and his colleagues had the following beautifully simple idea for how this can be generalized to situations where IID sampling is hard. They allow the proposal distribution at time t to depend on where the chain is at that time. That gives them a chance to move the proposal distribution around as the number of iterations increases. The proposal distribution moves. And that gives them the freedom they need to be able to create an algorithm that will work in high dimensions. So, here's how it goes. Here's my target. Maybe it has one of these long right-hand tail shapes we've been talking about. So that's our target, P of theta given y target distribution we're trying to sample from. Metropolis and his colleagues say, all right, suppose that you are, the last time you sampled, you arrived at the value theta star at time t. That's the last draw we drew. We recorded in the MCMC data set. Well, Metropolis et al. Say, I'm going to allow the proposal distribution to adapt to where we are right now in deciding where to go next. And so they put the proposal distribution on top of where we are now. And it might look like a normal curve, for example. In their original paper, they used uniform distributions that were centered at where you are now. But it's better, it turns out, to use normal distributions. And so this is going to be the thing that we're going to call the proposal distribution, as we talked about before. And I want to make sure I use the right notation for it so as not to get confused. Yes, I'm going to call this distribution G of theta star, given the data. And if you want, in all of this, I can drop the dependence on the data, because once we've got the data set, the target is just this density. It's just a function of theta. So I don't really have to put that part in. I don't really have to put that part in, but it doesn't hurt to put it in either. All right. So since it's a proposal distribution, let's propose a move. And what I mean by that is make a draw from a normal distribution centered at theta star t, and having some particular standard deviation for that distribution, which I'm going to call the PDSD. And it stands for Proposal Distribution Standard Deviation. Well, it could land any of these places that the normal curve thinks are possible. Suppose it landed right there. Suppose that's where I'm thinking of going. I'm thinking of moving here. Then what Metropolis et al. Want you to do is to compare the following thing. Compare the height of the target where you are now to the height of the target where you're thinking of moving. Notice that for the example I'm showing you here, the target is higher at the place I'm thinking of moving than where I am now. I'm going to call moves like that uphill moves, because they're actually moving to places of higher density in the actual target. Does it look to you from the picture that if we're trying to flesh out the actual target, uphill moves would be good? Sure enough, because by definition, the highest place, the place that the uphill moves would eventually take you to, is exactly the place where you want most of the draws to be sampled from. And so if you were inventing the metropolis algorithm in an ad hoc fashion, your first rule to yourself might be accept all uphill moves. And that indeed is true. And by an uphill move, I mean a place where the P of, I'm going to write it this way. Let's see. Let me make sure that it's consistent with later notation. Where the height of the density where I'm thinking of going, let me get rid of, I'll just call that theta star. That's this new place theta star, which I haven't given an index yet because I haven't actually moved there. Where the height of the density, the target density at theta star, divided by the height of the target density where I am now, where that number is bigger than 1. Okay, so far? That's an uphill move, except all uphill moves. Now let's talk about a downhill move. So I'm going to bring this down again a little bit. Suppose instead of thinking of moving here, suppose I'd taken the draw and it turned out that the theta star was down here. Do you want to accept intuitively, if you're trying to flesh out the actual target, do you want to accept all downhill moves? Well, maybe not, because then you'd probably be putting too much weight on the tails. And so that's item 2 in their algorithm. If it's an uphill move, it turns out to be an uphill move, they always accept it. But if it's a downhill move, they use von Neumann. They only accept it sometimes. And so they accept downhill moves with probabilities that are given by a particular acceptance probability, like von Neumann. So here's step 2. Accept any downhill moves with acceptance probability given by the same thing we had a minute ago. So there's what we had a minute ago. Now we're going to accept all downhill moves with acceptance probability given by P of theta star given y over P of theta star t given y. In other words, if it's almost not a downhill move, if this ratio is very close to 1, then you're going to accept it with high probability. But if this ratio is very small, as would occur if you're proposing a move way out into the tails, for example, then that's not going to be accepted very often, nor should it be, because it's way out in the tails. So far, I hope you'd agree with me that this algorithm is pretty intuitively reasonable. If you were inventing this yourself out of whole cloth, without trying to see if it had the right mathematical properties, I think you'd agree that you would do something like this so far. This seems reasonable. But here comes the really amazing part. Okay, rule number 3. If you accept right here, then of course theta star t plus 1 is just the place that you were thinking of moving. That's fine. But if you don't accept, now we have to invent a rule for what theta star t plus 1 is. And here's the amazing thing. They found that the right algorithm is arrived at by staying where you are for one turn. In other words, you count where you are now as part of the actual draws from the posterior distribution. Instead of throwing them away like von Neumann did, you keep them in the data, in the MCMC data set. And that's the part that most people wouldn't have been able to figure out just doing it intuitively. I think I can help you see, I can argue to you intuitively that it's good to accept all the uphill moves. And I think you would agree with me that you should not accept all the downhill moves because you'd end up overweighting the tails too much. And it makes sense then to accept the downhill moves with a probability proportional to how much downhill they are. That makes sense too. But now this is the real strange part. Obviously this is fine. If you accept, then of course the next draw is of course where you thought you were trying to go. But this is the part that I always find really hard to motivate. Why should, if you don't accept, why should you keep the next draw to be the same as where you are now and not simply discard and try again, for instance, like von Neumann did? But it turns out that the von Neumann thing at this moment is wrong, and this thing here is right. That's the algorithm. That's the Metropolis algorithm. We're done. That's it. Uh-huh. Oh, yeah. This works for virtually any target distribution, and it works for an extraordinarily wide variety of proposal distributions as well. That's fine. It doesn't have to be modified at all. And after lunch, I'll show you why. But basically, that's it. That's the algorithm in 3 little steps. Accept all the uphill moves. Uh-huh. He's got to put his finger on something important. I didn't say what the proposal distribution standard deviation is. And after lunch, I'll show you what effect it has on things. All choices of that number lead to valid MCMC samplers, to valid Metropolis samplers. But some of them are a lot more Monte Carlo efficient than others. And so that number, the PDSD, can be used as a tuning constant to try to optimize the Monte Carlo efficiency of the Metropolis algorithm. And that is something that we'll look at after lunch. And I've already eaten into lunch a little bit. So let's stop now and have lunch. We'll start again at 1:30. And wait one second. The video people, if you could turn off now from now until 1:30, that will save